Yeah. Oh. Yo, 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 yo. Oh. Alpha, beta, here we go. Learn with ease and let it show.
In this video, we are going to solve the West African Senior School Certificate Examination 2018 Physics Practical on simple pendulum. We will measure the time for 20 oscillations, calculate the period, and plot a graph of the period against the square root of the length. From the slope of the graph, we will then determine the acceleration due to gravity. Let's get started. You are provided with a retort stand with clamp, a meter rule, inextensible string, a stopwatch, a pendulum bulb, and other necessary apparatus. We are going to use this as a split cork. Suspend the pendulum bulb from the clamp as illustrated in the diagram. So in the diagram, this is the retort stand, and this is the pendulum bulb, and this is the string. So we are going to set up the apparatus as illustrated in this diagram. So first of all, we tie the string to the pendulum bulb. And attach the string to this object, which serves as the split cork. The main aim is to press the clamp tightly against the string to hold it. Adjust the pendulum bulb slightly such that AC is equal to L is equal to 90 centimeters. So we are going to adjust the length of the string such that the distance between the base of the split cork and the middle of the pendulum bulb is equal to 90 centimeters. We are going to measure with the meter rule. So we've already measured a distance of 90 centimeters from the base of the split cork to the middle of the pendulum bulb. We are going to displace the pendulum bulb slightly such that it oscillates in a vertical plane. When it moves from the point of release and comes back, it will be counted as one oscillation. And we are going to measure and record the time t for 20 complete oscillations. So when it goes and comes back, that will be 1, 2, 3, and on the 20th count, we stop the stopwatch and record the time for 20 complete oscillations. So we are going to release it and start the stopwatch at the same time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So time 1 for 20 oscillations is 38.47 seconds. And we are going to repeat it to determine another time for 20 oscillations for accurate results. So we displace the pendulum bulb and release it. Start the stopwatch at the same time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So the time 2 for 20 oscillations is 38.34 seconds. And we determine the mean time T for 20 oscillations. That will be time 1 plus time 2 divided by 2, which is 38.47 plus 38.34 divided by 2, which gives 38.41 seconds. So this is the mean time for 20 oscillations. And evaluate T, which is the period, and the square root of the length of the string. Now, T here is the time for 20 complete oscillations, but the period T is the time for one complete oscillation. So we are going to divide T by 20 to get the period. So the period will be 38.41 divided by 20, which gives 1.92 seconds to 2 decimal places. And for L, we have L to be 90.0 centimeters. We then convert it to meters by dividing by 100, which gives 0.9, but we leave it in 2 decimal places, so we have 0.90 meters. And we evaluate square root of the length. So square root of L, that will be square root of 0.90 meters. And the square root of 0.90 is 0.949. And the meters becomes meters exponent 1 over 2, since the square root is the same as an exponent of half. So we have the length in meters, which is 0.90 meters to 2 decimal places. This is time 1 in seconds, and it's 38.47 seconds. Time 2, also in seconds, is 38.34 seconds. And this is the mean time T in seconds. That is time 1 plus time 2, and the result divided by 2. We have 38.41 seconds. And we have the period also in seconds. That is the mean time divided by 20, and it's 1.92 seconds. And this is the square root of the length 0.90, and it gives 0.949 meters exponent 1 over 2. The unit should be written at the top here, and they should not be repeated with the values. If you write a unit at the top here once, that is all. You have to write the values without units in the table. So the unit comes at the top here. And we are going to repeat the procedure for 4 other values of L is equal to 80 centimeters, 70 centimeters, 60 centimeters, and 50 centimeters. So we are going to adjust the length of the string such that we have a length of 80 centimeters, which is 0.80 meters. Determine the time for 20 oscillations. Determine another time for 20 oscillations. Find the mean, evaluate the period, and evaluate the square root of the length. And we repeat it for 70 centimeters, which is 0.70 meters, 60 centimeters, which is 0.60 meters, and 50 centimeters, which is 0.50 meters, and tabulate the results. And we are going to plot a graph with T on the vertical axis and root L on the horizontal axis. So now, for the values of T, the first value is 1.92. And to plot 1.92 directly on the graph is going to be challenging. So we are going to move the decimal point 1, 2 to the right and record this as 192 times 10 exponent negative 2, and the unit is seconds, times 10 exponent negative 2, because we move the point twice to the right. So the next one, 1.79, we are going to move this point 1, 2 to the right, and we have 179. So the next one will be 168, the next one 155, and 142. For the values of root L, we have the first value to be 0.949, which is also going to be challenging to plot directly on the graph. So we are going to move the decimal point 1, 2, 3 to the right and record this as 949 times 10 exponent negative 3, because we moved it 3 times to the right, and the unit is meters exponent 1/2. The next value, when we move this point 1, 2, 3, we have 894. The next one will be 837. The next one 775, and the last one is 707. So we just want to see the values as whole numbers for easy plotting. That's why we adjusted them to standard form. So we are going to plot these values on the graph. So we draw the vertical and horizontal axis. And we are plotting T on the vertical axis. So we have T slash 10 exponent negative 2, and the unit is seconds, meaning we have converted the period to standard form by shifting the decimal point twice to the right for the values to look like whole numbers. And we are also plotting root L on the horizontal axis. So we have root L. Also, we have shifted the point 3 times to the right. So we have slash 10 exponent negative 3. And the unit is meters exponent half. And we are going to choose a scale for the graph. Looking at the values of the period, the least value is 142. And we've not been told to start from the origin, so we can start from 140. And we are going to choose a scale of 2 centimeters is to 5 times 10 is to the negative 2 seconds on t-axis. So we start from 140 and we add 5. So 145, keep on adding 5, 150, 155, 160, and so on. And for root L axis, we can start from 700 since the least value is 707. And we choose a scale of 2 centimeters is to 30 times 10 exponent negative 3 meters exponent half on root L axis. So we are going to add 30 to 700. We have 730. We add another 30, 760. We keep on adding 30. So on the vertical axis, the distance between each big box is 5. And 5 divided by 10 is 0.5. So each small box on the vertical axis is going to be 0.5, meaning 2 boxes on the vertical axis is equal to 1. And on the horizontal axis, the distance is 30. 30 divided by 10 is 3. So each small box on the horizontal axis is going to be 3. So this is going to guide us to plot the graph. The first point we have 192 on the vertical axis. 192. This is 190 and 2 boxes is equal to 1. So we count 4 more boxes after 190. And 949, this is 940. 1 box is 3. So 943, 946. 949. So 940 plus 3 more boxes. And they are going to meet here. The next one we have 179. So this is 175. 2 boxes is equal to 1. So we count 8 more boxes to get 4 added to the 175, making 179. And 894. This is 880. 1 box is 3. So 1 box will be 883, another one 886, another one 889, and the fourth one will be 892, and 894 will be in the next box. So they are going to meet here. 168, this is 165, plus 2 boxes is equal to 1. So we'll add 6 more boxes. So 165 plus 6 more boxes will give us 168. And we have 837 on root L axis. This is 820. And 1 box is equal to 3. So 823, 26, 29, 832, 35, and 37 will be within the next box. So they are going to meet here. The next one, 155 is here. We have 155 here and 775. This is 760. The middle is going to be 775 because we have 30 divided by 2, which is 15, added to 760 will give us 775. So they are going to meet here. The last point we have 142. This is 140. We want 2, so we move 4 times. Since 2 boxes is equal to 1. 707 on root L axis. This is 700, 703, 706, and 707 would be within the next box. So they are going to meet here. and we draw the line of best fit. Determine the slope S of the graph. So we draw these horizontal and vertical lines. These lines can be drawn at any point. There is no specific point to draw this line. But make sure the slope is as big as possible. We name here A, here B, and here C. The slope is change in BC over change in AB. For change in BC, that will be C minus B. So to get C, we draw this line and we have 183 minus B, which is 150. Remember, times 10 exponent negative 2 on the vertical axis, and the unit is seconds. And for AB, we have B minus A. B is 910 minus A is at the middle of 730 and 760. So we'll add 15 to 730, which gives 745 times 10 exponent negative 3, and the unit is meters exponent half. So 183 minus 150 is 33 times 10 exponent negative 2, and the unit is seconds. 910 minus 745 is 165 times 10 exponent negative 3, unit meters exponent half. And 33 times 10 exponent negative 2 is 0.33. The unit is seconds. 165 times 10 exponent negative 3 is 0.165, and we add the unit. And now 0.33 divided by 0.165 is 2. We have seconds at the numerator and meters exponent half at the denominator. So the reciprocal of meters exponent half will be meters exponent negative half. So this is the slope. Evaluate G is equal to 4 pi squared divided by the slope squared. So we have G is equal to 4 pi squared over S squared, where S is the slope. But pi is a constant, 3.142, and the slope is also 2 seconds per meters exponent negative half. So we replace them. And 4 times 3.142 squared is 39.49. 2 squared is 4, and the square will also affect the unit seconds. So we have second square. The square will also multiply negative 1 over 2, which gives negative 1. So we will have meters exponent negative 1 over here. And 39.49 divided by 4 is 9.87. The reciprocal of per meters is meters, since per meters is at the denominator. And we have second square at the denominator, so the reciprocal will be per second square. So G is equal to 9.87 meters per second square, which represents acceleration due to gravity. Now B part of the question. I. Determine from your graph the period of the pendulum for L is equal to 75 centimeters. So now the length of the string is 75 centimeters. We change it to meters by dividing by 100, which gives 0.75 meters. And remember, we plotted square root of the length. So let's find root L. That will be root of 0.75 meters. Square root of 0.75 is 0.866. Then we have meters exponent half. And remember, on the horizontal axis, we changed it to standard form by moving the decimal point 1, 2, 3 to the right. So we have 866 times 10 exponent negative 3, and the unit is meters exponent half. So we can draw a line on the horizontal axis at 866. So this is 850. One box on the horizontal axis is 3. So 853, 56, 59, 862, 65, and 66 will be in the next box. And we connect it to the period axis, and read the value over there. So from the graph, when L is equal to 75 centimeters, the period is 174, remember, times 10 exponent negative 2 seconds on the vertical axis. Now 174 times 10 exponent negative 2 is 1.74, and the unit is seconds. If the length of the string is 75 centimeters, the period will be 1.74 seconds. And BII, a simple pendulum bulb is set into simple harmonic motion. Sketch a diagram of the setup and indicate on it the position of A, maximum velocity, and B, maximum acceleration of the bulb. So this is the diagram. When you set a simple pendulum bulb in simple harmonic motion, the equilibrium position is going to be the maximum velocity, and the velocity is going to reduce until it gets to the end here, where we have the maximum acceleration and velocity becomes 0, and it repeats in that order. So this is the diagram. Thanks for watching, and don't forget to subscribe for more updates.
Alpha, beta, here we go. Learn with these and let it show.